Thank you very much. Thanks for the invitation. I will talk today about work on network science and triads. First thing first, what is a production network? A production network is a network made of users. So suppliers give some of their outputs, usually firms, give some of their outputs to users. They use them for their production process. This is the rigorous definition. And I will start by introducing what is that we know for triads and production networks, why they are important. Then I will go to the dataset description of the Statistics Netherlands dataset of production networks, and then I will finish with the results that we arrived to. So what do we know? Production networks are usually available at firm level only for some nations. For example, Hungary, Brazil, Spain, France, and or they are reconstructed from aggregated data, usually coming from industries, also at a not so granular level of industry sector. So what we know is usually taken from the few data sets where we have real data, even if with some limitations. For example, from the Hungarian data set, we know that often triads, so triads that are formed, for example, with the suppliers that are connected to two users, or B triads, occur more in absolute value than closed triads. Then we refine the analysis in literature. They refine the analysis comparing this value with a random expectation given some random model, and they saw, for example, in the Japanese production network, there is that open triads occur more than random, while closed triads occur less than random, and finally, in the Dutch reconstructed production network of 2012, they saw that across different commodity layers, the production networks are more bipartite than random. So what is the moral here? The moral is that according to the knowledge, for example, using not different commodity layers, but only one representative commodity, so putting everything in not a multiplex, but a monopartite network, we have that the connections are not driven by similarity as in social media, where triangles are very predominant, but are more driven by complementarity needs. So I need something, you need something else, let's do a contract and let's exchange. What instead I will see here is the CBS Statistics Netherlands data for 2018, where we have an enrichment, where we have some data taken thanks to surveys about the commodity layers. So we know what the suppliers give and what users give with a certain granularity, so with a certain specifics. And what we start from is a firm level network of 900,000 firms for 650 commodity layers. However, this is reconstructed from various sources. For example, taking as in consideration statistics from other countries, and moreover, it is based on a matching that is given by the deterministic procedure that has been shown to bias both degree centralities and the number of links. However, in our framework, we will use these measures, so we have to aggregate at inter-industry level. So we will use a network of 862 industries for 187 commodity layers. So, and this data is more reliable because it is adherent with the Eurostat data. So we have a more reliability on the results. So you can imagine this this network as a multiplex network of 862 industries across different commodity layers. So in each commodity layers, you have suppliers of that good and users of that good. And our objective, as I said before, is to characterize if for each of these motifs in the figure P, we have more occurring the random motifs for each of these types, and we will characterize also the fluxes. So we will characterize even if on each motif there is an expected high or low amount of Meinden. And we can do that thanks to random null models that can take into consideration the directionality of connection and also the reciprocity of connection. For example, here we have a directional null model that is based on the maximum entropy framework, where we want, our goal is that of determining the distribution of links and distribution of weights. So what we do here, we take into consideration the direction of the connections, so outward and inward connections. And we, for the binary part, so in order to obtain the distribution of links, we maximize the binary Shannon entropy, PA, ln PA. While for the distribution of the weights, we proceed in a Ardle model manner. So we maximize the conditional Shannon entropy of the weights, so of the weighted graphs, QWA, given the binary configuration. So first we maximize the binary Shannon entropy, then we maximize the Shannon entropy for the distribution of weights given B. In the case of the directional model, we have directional constraints. There are the out degree, so the number of partners of the suppliers, the in degree, so the number of partners as user, and then also the out strengths and in strengths. There are just the sums of the weight outgoing and the sum of the weights ingoing for each supplier and user. And then we can enrich this model, taking into consideration also reciprocity. So we use the same framework, but here we take into consideration more constraints. So as you can see on the right, the connection can be divided in 4 events. The absence of connection, this is the last one, or the non-reciprocated outgoing connection, the non-reciprocated ingoing connection, and the reciprocated connection. And so with this analogy, we can write the non-reciprocated outward, non-reciprocated inward, and reciprocated degrees as the sums of these connections. And then we can formalize also the strengths that will be the outward, the non-reciprocated outgoing strengths, the non-reciprocated ingoing strengths, and then 2 cases for the reciprocated strengths that are the outward connection from for example, a supplier, the sum of the outgoing weights from a supplier on reciprocated links, and the same but ingoing still on reciprocated links. The problems are separable, so you still can maximize the Shannon entropy for the binary part, and then for the weights. So what we obtain? What we do is compare the empirical, for example, occurrence of a specific triad with the expectation divided by the standard deviation. So we just do a z-score analysis. In this case, the confidence interval will be given by 500 realizations of our graph ensembles, and this analysis will be given for each of the commodity layers. So we will analyze each commodity layer separately. In doing so, we will have, for the binary analysis, so for the analysis of occurrences of the different triads, we have on the top the aggregated network. This is just the collapse of all the commodity layers into one, just to see the comparison. And on the left, we have the results of the z-score analysis for the directional null model. On the right, with orange, or the reciprocal null model. And the transparency that you see is the confidence interval of 95%. So what we see here is that for different models, first, going from a directional model to a reciprocal null model change the kind of motives that deviate like have an occurrence that is unexpectedly high or unexpectedly lower. And then you can find that usually there are a lot of peaks, so a lot of deviating motifs in the aggregated case. However, when you go in different layers, across commodity layers, you can see on the left the counter-cumulative distribution of the deviating occurrences. And you can see here that, for example, for the reciprocated null model, 52% of the commodity layers have no deviating motifs. So they behave as expected for the triadic patterns, while usually other 32% have one or two motifs at most. So, what is the type of motifs that we detect? Then on the B and C figures, so you can see the different type of motifs. CH, it is the number of commodities for which that kind of motif is higher than expected. CL instead is for which kind of motif? For the number of commodities for which the motif has a lower than expected occurrence. And what you can see here is that it's not obvious that there is a sort of open-closed triad dichotomy in this case when you go into single commodities, but usually the spectrum is more heterogeneous. So that we can say that each commodity has its specific triads and are characteristic of the commodities and should be analyzed at the commodity level. Then we go into the weighted analysis. So here, instead of occurrences, we are seeing the flux on the triads. And what we see here, for example, in the representative aggregated network, where all commodities are collapsed into one, is that for the CR-VCM, that is the model with reciprocation, we see that a lot of type of motifs are well reproduced in random. However, when we pass to commodity layers, we see a similar structure as in the binary analysis, so that 52% still have no deviating motifs, and there is another 33% that have one or two motifs. And when we pass on figures B and C, we see the predominance of one type of motif, that is motif 1. For example, here you can see that for 42 commodities, motif 1 is higher than expected. What does it mean? It means, for example, here you say higher than expected. Instead, if you go for the binary analysis, it behaves always as random. So it means that motif 1 that is composed of one supplier and two users behaves as expected in occurrence, but the suppliers are giving unexpectedly high amount of money on this motif, on these triads. And that can be a signal that a supplier is controlling that specific market and should be investigated more. Okay, and then we still see, even if not for the motif 1, we still see heterogeneity, and then other than motif 1, one should see in the commodities which are the characteristic motifs of that commodities. Finally, this analysis can be seen in depth for each single commodity. We will see here for the first in revenues, that is other machine devices and components, that is the first commodity revenues in the Netherlands, that take into consideration also semiconductor companies that are very relevant in the Eindhoven area, for example. And you can see here the distribution, the out degree and in degree distribution on the left, the out strength and in strength distribution. And you see that even if there are a high amount of suppliers and users, usually the volume are concentrated in the top 20. For example, you can see here 84% for the percentage of out strength and 71% of in strength are in the top 20 users. And you can find you can do this analysis of Z-score for the number of occurrences and the flux on triads. And you can see here on the left the absolute numbers, so the number of occurrences and the flux of on each motif. And on the right, the result for the reciprocal null model. For example, on B, we can see here that the only motif that deviates higher than expected is the 9, that is given by the leverage cycle, that is being shown, at least in financial network, to be critical because the leverage cycle, so cycling relationships, can easily collapse because of one bankruptcy. And on D, we can see instead a higher than expected motif 1. So in order to have the complete picture, we cannot maintain only the binary analysis, that is what is usually done in the literature, but we need also the weighted one to understand if there is a control in fluxes, and it can give also a help to understand not only shocks due to bankruptcy or loss of connection, but also shocks due to a reduction of input or use. So conclusions. We analyzed triadic structure and triadic fluxes across multiple commodities. We showed that for 52% of commodity layers, they're not unexpected triadic structure or triadic fluxes, and for 85% of commodity layers, they usually have two or one type of triadic deviations or triadic motif deviations. And we also develop a comprehensive package for sparse and not sparse networks to do this analysis. And thank you very much. I want to thank my collaborator, Diego Laschelli, and happy packages.
Thank you very much. Are there any questions from the audience?
I have just a curiosity. When you consider the model as separate, right? Let's say that you maximize the probability of the adjacency matrix and then conditional to the adjacency matrix, the probability, the entropy of the distribution of the weight. What kind of distribution do you get? Is it the hypergeometric one, like in the standard sparse case, full case, or you have some other kind of solution?
So in any case, usually it depends on the type of weights that you want to put.
Okay.
In this case, we put continuous weights.
Okay.
So you have the logistic for the binary part,
yes,
and the exponential for the
so you
for the continuous part. If you have the discrete part, if you have discrete weights, instead it will be geometrical.
Yeah. Okay. So the size that is the distribution, right? That is the exponential in this case.
Depends on the constraints. So these constraints is exponential.
Okay.
So it totally depends if the constraints are linear.
Okay. Okay.
But in any case, for instance, you fix by yourself. So
you given the nature of Shannon entropy for the weight, you get the exponential.
Yes.
It is the question.
Yes.
And in the discrete case, so maybe I missed this point, you get the
geometric.
geometry. Okay.
okay. Thank you very much again, Marzio.